All right, let's continue our notes here. We're going to do this quick check problem from Wednesday. And of course, you know, we have two things we need to do. We need to graph it, and we need to use the theorem on limits of rational functions. Okay, so if we graph this, we're going to use numbers that are 2 or less, but not including 2, right? So if we use that, at 2, we should get 1, and it should be an open circle, okay? If we use 1, we should get -2, and of course, if we use 0, we should get -5, okay? And if we connect those dots, let's see, if we connect the dots, okay, that's one arm, and we need to draw the other. So, of course, again, at 2, and we can use exactly 2 here, that's going to give us 5, closed circle. And we need 1 or 2 more points. If I use 3, I should get 7. And if I use 4, I should get 9. Okay. And now we have our piecewise function. Now that we've graphed it, we need to take a look and see if we can tell if the limit as x goes to 2 from the left of 3x minus 5, will that be equal to, question mark, the limit as x goes to 2 from the right? And we'll use the function 2x plus 1. All right, let's take a look. I'm hoping that it's going to be continuous, but it might not. Okay, so here we're going to have 3 times -2 minus 5. That's going to give us 1. Oh, excuse me, not -2. Sorry. So 6 minus 5 is 1. Here we're going to have 2 times 2 plus 1. That's going to give us 5. Clearly not equal. Therefore, G is not continuous at x equals 2. All right, let's keep going with our notes. Example 10, very similar situation going on in example 10. Okay, again, you know what I'm going to say. I'm going to say graph it for example 10, and we see that we also have another piecewise function, and we're going to check 2. So if we do that, that's going to give us 1, closed circle, and we need some more points that are less than 2. If we use 1, we should get 2. If we use 0, we should get 3, and so on and so on. But let's try one more. -1 should give us 4, and now we can connect our dots. We have a function going this way. Now let's try for numbers that are not including 2. If we use 2 but want to write an open circle, let's see. 2 squared is 4. 4 minus 3 is 1. It happens to land in here, which is already a closed circle, so we can just keep going. Let's try 3. 3 squared is 9. 9 minus 3 is 6. And now we have some points, and it should be heading out that way. Now that we have that, of course, we're going to try for the limit as x goes to 2 from the left, and the limit as x goes to 2 from the right. Also, we need to check whether or not g of 2 is in there as well. So let's take a look. We can do g of 2 very quickly. Okay, when it's exactly 2, okay, we should get 1. Okay, let's take a look at this. The limit as x goes to 2 from the left, we're going to use this function That means we'll have negative 2 plus 3, which is 1. And we're going to use 2 from the right. That means we'll end up with 2 squared minus 3. That's going to also give us 1. This is excellent. So now, by the theorem, we can say that limit as x goes to 2 of g of x is also equal to g of 2. Therefore, the function is continuous. All right, let's take a look at checkpoint problem number 4. Checkpoint problem number 4, of course, you know and I know that we're going to graph it. Remember, we need to simplify this particular arm to x plus 3. Okay, we have an intercept at 3, slope of 1. Okay, connect the dots. Please use a ruler, unlike myself. However, not at 3. We need to have an open circle there. And for our second portion, we need to graph 3, 7. Okay, now we need to take a look. I have a hunch that this is not going to be continuous, but let's follow through with our rules. The limit as x goes to 3 of h of x, it should be equal to h of 4. Excuse me, h of 3. So we can see that the limit as x goes to 3 of h of x, pardon my drawing there, so that's going to give us 3 plus 3, which is 6. And we can see that h of 3, that's going to be 7. Again, we have one of those cool, easy problems where we can see what it's going to be. And since 7 does not equal 6, we can say that this function not only does not exist because they're not equal, it is also not continuous. All right, that takes us to our next example, example 11, which is for our business majors out there. I'm going to stop at number 11 and leave quick check number 5 for yourself. But on number 11, we're going to take a walk through with number 11. We need to, of course, graph it. I would highly recommend that your intervals be by 100. So let's have this be 0, 0. I'm going to let you graph it on your own so that you can get used to doing that. It won't take long. And so, et cetera, et cetera. I'm going to let you graph and continue that. And this also, this particular axis can lend itself to by 100s as well. I'm going to let you graph that part. Okay, so make sure you graph it. And of course, our primary concern is whether or not P is continuous when X is 500 for this particular problem about decorative rocks and selling it by the 500-pound sections. So is the limit as X goes to 500 from the left, will that be the same as the limit as X goes to 500 from the right? Okay, from the left, we're going to be using this function, 2.5x, and from the right, we'll be using 2x. If we plug in values, 2.5 times 500 will give us 1,250, and here we will have 1,000. Okay, I think it's clear after the number of examples that we've seen so far. If these two are not equal, the functions do not exist, and it's not continuous. So, not continuous at x equals 500. Okay, and that's going to be it for tonight. Again, I need you to do quick check number 5 by yourself. You're welcome to graph it, but I'm interested in seeing these 3 limits. The question will be, is it continuous? I think so.